John, I'm starting on slide 5. You're going through 1 through 4.
She said go.
She said go.
Okay, so my name is John Noble, and my group members are Thomas Briscoe and Thomas Hale. Our advisor is Dr. Gates, and the project we are working on is an externally launched expanding wing VTOL drone. Um, and let's begin. So our problem definition is that we have multiple issues. Oh, I'm sorry. My thing's all messed up. Oh no, okay. I'm sorry, we're good. Uh, so there's multiple issues with existing inspection drones that we have in industry. For example, fixed wing drones provide excellent range and efficiency, but are incapable of taking off and landing in confined and restricted spaces. Restricted spaces include things like power line trails that don't have flat, long, and obstruction-free runways for fixed wing drones. There's tree branches, power line poles, all sorts of things. Um, Therefore, it's critical that a drone is able to take off and land in a vertical fashion. In regards to increasing efficiency at takeoff, it's possible to attach the drone to a rail system and use an external system, such as like a launcher, to propel the drone into flight. The drone may have its wings folded at launch to maximize the aerodynamic efficiency and minimize drag. And combining the range advantage with the fixed wing drone with the takeoff and landing capabilities of a quadcopter drone can drastically increase effectiveness for all types of users. So our design constraints for this project vary greatly and depend a lot on the availability of materials and the budget of the project. So first and largest of the constraints is the cost, and there are four main costs. The material of the expandable wing, the four propellers, and the mounting costs for the propellers and camera, as well as the vertical drone launcher. The material of the wings will be constrained due to previously understood industry standards, such as fiberglass and rigid foam. Those are, widely found to be the most effective at cutting weight and decreasing cost. The propellers, the constraints will be based on the amount of propulsion needed to achieve lift and have a precise flight and landing sequence. Mounting costs are probably going to vary and may not actually be that high, basically because we're the ones doing the work. But that's going to be constrained to the size and shape of the propellers and camera, and that's going to contribute to the total weight limit. The launcher cost is going to vary due to the decision to buy an existing product or to create one ourselves. And then the testing cost is going to be limited to the practicality of testing and the prototype model, and trying to avoid breaking it every time it's tested. The last cost constraint is for the controller, receiver, and wiring for the flight controls, which we hope to keep down because, as we mentioned in previous presentations, Dr. Gates has a wide array of used drone parts. The constraint that the software constraint is another one, and that's going to be used for designing and building the drone. The software needed to is provided by the school or already acquired by the team, but it's going to be difficult to obviously get into school to use it. So we're going to try and get some of it at home. And then the last area of the overall design constraints are the FAA and customer requirements. So the drone has to be under 55 pounds, and the customer design requirements will be designing the drone to be able to take off, fly, and land in small areas. And then the target users are going to be survey and construction companies. People who need to survey lands that are too dangerous to enter, too large to inspect as an individual, or require an aerial view to gain the largest amount of information. Inspection survey companies would gain the most by utilizing this piece of equipment. As its minimal needed takeoff area, it makes it useful in cities, populated areas, and previously mentioned power line areas. Farmers would be able to utilize this drone for pesticide dispersal systems, as well as being able to survey their land without needing to physically travel. Finally, the drone style would be able to give recreational users a way to take aerial pictures and photos, or tourist companies to promote their travel destinations.
All right. Hello, my name is Thomas Hale. There have been a couple pretty previous iterations of this project, but it's a pretty novel project. It takes components from other previous projects and kind of combines them together. Um, the quadcopter drones have been done many times at CCSU, and we will not be taking a lot from that design, but the entire chassis and airframe will be different from the standard quadcopter formation. The main thing that they are going to share is the four rotors. An expanding fixed-wing drone has been successfully prototyped, and we will continue to develop it by adding vertical landing capability to the drone itself. Um, the design of the drone includes an external catapult for initial launching, with expanding wings that will expand as it flies through the air after initial launch. Um, we plan to continue the project by modeling the expanding wing drone in AutoCAD or NX, and adjusting the design from there to incorporate any extra rotors and any other design constraints necessary. Next page. Sorry if mine's lagging. The literature survey. The problem has been partially solved in the past, particularly at CCSU. A student has completed a design project several years ago when they designed a fixed-wing drone capable of folding its wings and being launched from a catapult. The exact details and specifications have not been provided to us by Dr. Gates, but we are in the process of obtaining them and building the foundation for our drone from this information. On an industrial scale, Lockheed and Robotnik teamed up to create a tactical drone launcher capable of launching drones into flight from small areas not suitable for traditional runways. In addition, on a smaller hobbyist scale, a company called UAV Factory has a product that is designed to launch for drones up to 77 pounds. Our drone is only going to be 55 pounds, so it shows you that we are well within the capabilities of even recreational use. The catapult uses a pneumatic piston to propel a 55-pound drone off the rail at 21 meters per second. And now we have our team members, as mentioned before at the beginning of this presentation. It is myself, Thomas Hale, John Noble, and Thomas Briscoe as part of this team. My personal strengths include structural analysis, proficiencies in MATLAB and NX, as well as machining. My weaknesses including coding, time management, and I tend to be a bit scatterbrained. I've had multiple classes involving NX and MATLAB, requiring me to become proficient in both those softwares. So they have allowed me to become proficient and see the strengths and weaknesses with using either of them. I've had multiple classes with structural analysis. So the years of having those classes and being exposed to that level of or that style of engineering has given me a level of proficiency in that I deem as a strength. In addition, I served last year as a machining lab assistant for the entire year under both Dr. Moore and another professor. I'm blanking on his name in the fall. Not Godsey. He's a different professor. Rudnick, Professor Rudnick. Thank you. And I was able to learn more from them further outside of what 217 teaches and hone the skills of machining. So I consider that to be a strength. Coding, I am very weak in coding. I have little to no exposure to any coding languages, not C++ or anything, not Python. I am very weak in any coding. Time management, I tend to procrastinate. I'm very weak in that sense that I tend to procrastinate. I tend to put off assignments. In addition, I'm very scatterbrained in the sense that I work on whatever my mind is on at the time. If it's difficult for me to focus on something at a time, I will move on to something else, which will lead me to have many half-finished assignments rather than one completed assignment. So it tends to be I can't focus on a single project for an extended period of time.
So, John Noble here. Since we're not doing this in person, my strengths again include using modeling software such as NX and AutoCAD. I'm good with ANSYS for FEA, and I have a good I have an eye for detail and a lot of experience in building and construction. which comes in handy when I'm working with my hands. I think this is going to be very useful for the initial stages when we are modeling our drone and running different sorts of analyses on it, and then the ability to work with my hands when it comes to the actual assembly of the prototype. My weaknesses, like everybody in my group, is time management. So this should be an interesting semester and following semester. And I don't like to code. I know how to code. I did a couple years of computer science in school. I know how to do it in a couple different languages. I just really hate it. Luckily, most of the coding is taken care of with the ArduPilot software we'll be using. And again, in related to time management, a bit of a procrastinator, so that does not help.
Hi, I'm Thomas Briscoe. My main strengths lie in like overall computer use, just like the aforementioned. Mostly being AutoCAD inventor with a bit of NX, going back to starting in high school, using CAD software all throughout. I also have completed the FEA class at CCSU, and I'm proficient in using the ANSYS software. And as far as work experience, I've worked at a mechanical engineering firm over the past 2 semesters, full and part-time. So it's given me a good insight and knowledge of how workplace projects and tasks are professionally completed in a timely manner. And just like John, I've also worked in construction and used my hands to build things, which will definitely come handy in this project. As far as weaknesses go, most of them revolve around time availability and time. Since I'm taking 5 classes as well as working part-time / full-time throughout the year. Another problem, it's probably just as big, is that my organization skills are lacking when compared to my peers. I tend to keep all information for a specific task or project together rather than breaking it down into sets that would help efficiency and finishing of the project on time. Next slide.
It's on the next slide.
It lags a little bit. As far as tasks go, the tasks for this semester include researching a current single wing or expanding wing vertical takeoff drone designs, as well as assessing the strengths and weaknesses of such designs. And then to turn the current prototype available from Dr. Gates into a CAD model, as well as then adjust the current prototype into the design constraints that we set and have been set for our project, and adjusting as needed, as well as determining the proper parameters for the FEA model. The prototype or the design that we are going for is larger than the original prototype that Dr. Gates has. So proper parameters, including any power constraints, the weight of the drone, and any proper parameters for the FEA model itself. And then go further and perform an analysis on that model itself, and see what requirements as far as power from the motors are required for a larger scale design, as well as assemble a prototype model. However, we plan to do that, whether it be machining in metalworking or create another version of it, but to create a assembled prototype model to get a visual of what we are aiming for, and finally to test the prototype if it were to be a working prototype. And then, so our research tasks would include researching the design in the single wing VTOL drone design. Analysis tasks include modeling the current prototype, adjusting the model, and then modeling it in FEA and performing an analysis there. And then manufacturing tasks, would include assembling a model prototype, possibly not capable of flight, but to show a initial design of the prototype with dimensions that are proportional to that of the prototype design. The next slide.
Okay, so as far as tasks completed, due to numerous events outside of our control, progress on this project has been limited. So So we've pretty much completed all of the research necessary to move forward with modeling on the FEA and the actual prototype model. At the start of the semester, we had two complete design changes due to unavailability, the first two, which required us to slightly change our research goals. After finally settling on the design, the two main areas of research went into the VTOL design of the drone and the actual catapult launching device. First, we took a look at the previous senior projects done with VTOL drones. Most of them were not vertical takeoff, or they were, I'm sorry, they were not launching straight up as far as using a catapult. And we used it to look at possible ideas and find what was the most significant difficulties they faced. We found good resources for the launcher, as previously mentioned, at Martin and Robotic Tactical Drone Launcher to show what a large scale launcher would look like, and then narrowed it down to finding the UA factory portable pneumatic catapult, which would be something that we would buy or design ourselves. And we were thinking it would be even more of a vertical takeoff than the previous shown. Lastly, we researched like commercial products that would have to that are out there right now, coincided with our final design project. We came across a company called Wingtra that had a very good example of what we were trying to do and had numerous examples of different types of VTOL drones. Although the company does not use vertical drone launchers like we planned to, it had descriptions of the advantages and uses of VTOL drones that were beneficial to our design concept. So this is our overall timeline, Gantt chart for the semester. Currently, the only possible task to continue working on, which I said we completed, is the research, as we are now quarantined and can't get on campus to the equipment, or meet with Professor Gates to narrow down the next steps as far as modeling and the parameters for the FEA prototype. The rest of the tasks that we have to complete for this semester would be to model the components, redesign the prototype that Dr. Gates has already made, determine proper parameters for the model, actually FEA the model, and then build the construction, whether it flies or not, and then a proposal and presentation by the end of the semester. If you look at the chart, you can kind of tell that we obviously haven't been able to keep up with the weeks that we have stated for each individual task. We're hoping that we can catch up with talks with our advisor. Next slide. So as far as the overall project, I feel like we have a good grasp on looking to do and build and have a final concept and design, but are stagnating on actually to go about or how to go about completing the next tasks on our list. We're hoping that our advisor, Dr. Gates, has some ideas on how to acquire the necessary software and modeling aspects that we need to progress. And we have a meeting with him in the near future to hopefully get the ball rolling. Thanks for listening. And that's it. We have